Proxima Centauri, the nearest star to our nearby planetary group, has for some time been a subject of interest for cosmologists. This small red dwarf, discovered in 1915 by Scottish astronomer Robert Innes, is part of the Alpha Centauri system, which also includes Alpha Centauri A and B. Despite its proximity, just 4.24 light-years away, it remains invisible to the naked eye due to its relatively low brightness. However, Proxima Centauri holds immense scientific value, especially as the host star of Proxima b, an exoplanet that orbits within the star's habitable zone. Red dwarfs like Proxima Centauri are smaller, cooler, and significantly longer-lived than stars like our Sun. Their low glow makes them challenging to observe, but it also means their habitable zones are much closer to the star. For Proxima Centauri, this translates to an orbital distance of 0.05 astronomical units, a mere fraction of the distance between Earth and the Sun. This proximity exposes Proxima b to intense stellar activity, including frequent solar flares and high levels of radiation, creating an environment quite different from Earth's. The discovery of Proxima b was a great achievement in exoplanet research. Using the radial velocity method, astronomers detected subtle wobbles in Proxima Centauri's position caused by the gravitational pull of an orbiting planet. These wobbles allowed scientists to measure the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the presence of Proxima b, marking a breakthrough in the search for potentially habitable worlds beyond our solar system. While ground-based observations have provided valuable insights into Proxima b, they come with significant limitations. Atmospheric distortion and light interference hinder the ability of Earth-based telescopes to capture detailed data about the planet's surface or atmosphere. Most of the information we have, such as its mass, distance from the star, and orbital characteristics, relies on indirect measurements. To uncover further details about Proxima b's environment and its potential for life, advanced observational tools, like the James Webb Space Telescope JWST, are essential. Proxima Centauri's role as a gateway to understanding exoplanetary systems cannot be overstated. As the closest star system to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima b, in particular, represents an enticing possibility, a rocky, Earth-sized planet with the potential to harbor water and perhaps life. However, the challenges posed by its harsh environment make it a complex puzzle for scientists to solve. The James Webb Space Telescope JWST isn't just another tool in the field of astronomy, it is a revolution. Designed as the successor to the Hubble Space Telescope, JWST was conceived to address the limitations of its predecessor and push the boundaries of human knowledge. While Hubble has provided invaluable insights into the universe, its capabilities are constrained by its focus on visible and ultraviolet light. JWST, in contrast, is built to observe the universe in infrared wavelengths, allowing it to peer through cosmic dust and reveal phenomena invisible to Hubble. One of JWST's key design features is its primary mirror, which spans an impressive 6.5 meters in diameter, more than twice the size of Hubble's mirror. This larger mirror enables JWST to gather significantly more light, making it capable of observing extremely faint and distant objects. Coated with a thin layer of gold to enhance its infrared reflectivity, the mirror is composed of 18 hexagonal segments that work together to create a highly sensitive observational platform. Another groundbreaking advancement is JWST's 5-layer sunshield, which keeps the telescope's instruments at a steady temperature of about -233 degrees Celsius. This ultra-cold environment is crucial for detecting faint infrared emissions without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point L2, a stable position roughly 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain continuous observations. The telescope can study everything from the earliest galaxies to the atmospheres of exoplanets, like Proxima b. Its focus on infrared light is particularly significant, as it allows astronomers to study redshifted objects, those whose light has been stretched to longer wavelengths as the universe expands. JWST's capabilities extend far beyond mere observation. It is designed to answer some of the most profound questions in science, including the origins of galaxies, the formation of stars, and the conditions that could support life on other planets. With its state-of-the-art instruments, including the near-infrared camera NIRCam, the mid-infrared instrument MIRI, and the near-infrared spectrograph NIRSpec, JWST is not just a telescope. It is a time machine, a laboratory, and a testament to human ingenuity. Proxima b has captivated scientists and the public alike as a potential second Earth. Situated within the habitable zone of its star, the planet has the right conditions to potentially support liquid water, a crucial ingredient for life as we know it. With a mass approximately 1.17 times that of Earth, Proxima b is likely a rocky planet similar in composition to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima b is far from an ideal twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual daylight, while the other is in eternal darkness. This creates a unique environment with extreme temperature differences between the two hemispheres. The region where day meets night, known as the Terminator line, might offer a narrow zone with conditions mild enough to support life. The challenges posed by Proxima b's environment are significant. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which can emit bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima b retains any atmosphere, it likely requires a strong magnetic field to protect it from radiation. Without such protection, the surface environment would be hostile to life as we know it. Despite these challenges, scientists remain optimistic about the potential for life on Proxima b. Its position within the habitable zone suggests that liquid water could exist, either on its surface or in subsurface reservoirs. Life could adapt to the harsh conditions, much like extremophiles on Earth, organisms that thrive in extreme environments, such as deep-sea hydrothermal vents or high radiation zones. These adaptations could include radiation resistance, subsurface habitats, or unique biochemical processes. The search for life on Proxima b is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions. Are we alone in the universe? Proxima b represents a tantalizing possibility, a rocky, Earth-like world that could harbor the conditions necessary for life. As our technology advances, so too does our ability to explore this fascinating planet and uncover its secrets. While Proxima b presents exciting possibilities, its environment is heavily influenced by the nature of its host star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf, smaller, cooler, and significantly less luminous. Its reduced size and temperature mean that its habitable zone is much closer, pulling Proxima b into an orbit just 0.05 astronomical units from the star, about 20 times closer than Earth is to the Sun. This proximity creates a unique set of challenges for the planet and any potential life it may host. One major issue is Proxima Centauri's stellar activity, particularly its intense and frequent solar flares. These flares are sudden, powerful eruptions of energy that release high doses of X-rays and ultraviolet radiation. Such events are far more common and energetic in red dwarfs than in stars like our Sun. For Proxima b, this means a constant bombardment of high-energy particles, which could strip away the planet's atmosphere over time. Without a protective magnetic field, any atmosphere on Proxima b would be vulnerable to erosion, leaving its surface exposed to harsh radiation. Even if Proxima b retains some of its atmosphere, the radiation from Proxima Centauri poses serious challenges to life. High levels of ultraviolet radiation can break molecular bonds, preventing the formation of complex organic compounds. This would severely limit the potential for life to develop or sustain itself on the planet's surface. On Earth, Organisms like Deinococcus radiodurans have evolved mechanisms to repair DNA damage caused by radiation, suggesting that life on Proxima b could similarly adapt. However, the level of radiation resistance required would be extreme, potentially requiring entirely new biochemistries. Interestingly, Proxima b's tidal locking might offer some protection. While one hemisphere faces constant radiation from Proxima Centauri, the planet's dark side could serve as a refuge. Subsurface habitats or deep caves could shield potential life forms from the worst of the radiation. Similarly, if Proxima b has subsurface oceans, they could provide a stable, radiation-free environment where microbial life could thrive, much like the ecosystems around hydrothermal vents on Earth. Despite these challenges, scientists remain hopeful that Proxima b's extreme environment provides a unique opportunity to study the resilience of life. By understanding how organisms could survive or even thrive under such conditions, researchers can expand their understanding of what makes a planet habitable. Proxima b is not just a potential home for life. It is a natural laboratory for testing the limits of life itself. The planet's proximity to Proxima Centauri also raises intriguing possibilities about its atmospheric composition and surface conditions. If Proxima b has managed to retain a thick atmosphere, it might help distribute heat more evenly across the planet, reducing the extreme temperature differences caused by tidal locking. This could create stable regions, particularly near the Terminator line, where temperatures are moderate enough to sustain liquid water. Scientists speculate that these regions might host unique ecosystems, shielded from the worst effects of stellar radiation. Moreover, subsurface environments could offer additional protection. Just as Earth's deep-sea hydrothermal vents support life in the absence of sunlight, similar environments on Proxima b might harbor extremophiles adapted to high-pressure, low-light conditions. These organisms could rely on chemosynthesis, a process that uses chemical energy rather than sunlight, to fuel their metabolic processes. Such adaptations would broaden our understanding of life's potential to thrive in extreme and alien environments. The exploration of Proxima b is not just about the search for extraterrestrial life. It also offers valuable insights into the evolution of planetary systems. Red dwarf stars like Proxima Centauri are the most common type of star in our galaxy, and their habitable zones are markedly different from those of sun-like stars. Understanding the dynamics of planets orbiting red dwarfs could provide a broader context for the habitability of exoplanets and the potential prevalence of life in the universe. Future missions and advanced technologies will play a crucial role in unraveling the mysteries of Proxima b. The James Webb Space Telescope JWST, with its unparalleled infrared capabilities, is expected to provide more detailed observations of Proxima b's atmosphere and surface characteristics. If JWST detects signs of atmospheric gases such as oxygen, methane, or carbon dioxide, it could be an indicator of biological activity. However, distinguishing between biological and geological processes will require careful analysis and follow-up observations. Additionally, proposed space missions, such as Breakthrough Starshot, aim to send lightweight probes to the Alpha Centauri system. These probes, traveling at a fraction of the speed of light, could potentially reach Proxima Centauri within a few decades. Equipped with miniature cameras and sensors, they could capture close-up images of Proxima b and gather data about its surface, atmosphere, and potential habitability. Such missions represent the next frontier in interstellar exploration, bringing us closer to answering the profound question of whether life exists beyond Earth. In conclusion, Proxima b remains one of the most compelling targets in the search for extraterrestrial life. Its proximity to Earth, combined with its position within the habitable zone of Proxima Centauri, makes it a prime candidate for further study. Despite the challenges posed by its harsh environment and intense stellar activity, the potential for discovering life, or understanding the conditions necessary for life, makes Proxima b an invaluable subject for scientific investigation. As technology advances and our observational capabilities improve, we stand on the brink of a new era in our quest to explore the cosmos and uncover the secrets of distant worlds.